So please stay with me. I'm going to record just so I can post this recording later. If there's something that I said during class time that you wish you could hear all over again, you will have that opportunity to hear it again on the recording. I recommend, if you're watching a recording, sometime again, that you do it at 1.5 or maybe double speed. I annoy myself when I watch myself recorded that I'm going so slow. And certainly if you're, going through class a second time just to pick up on something you may have missed, there's probably plenty of stuff you didn't miss, so you could speed it up and go through a little bit faster. So I would recommend that, just so I'm less annoying to you, because who wants that? The textbook for this course is free and online. It's OpenStax College Physics. If you wanted to go to OpenStax, if you wanted to go to OpenStax yourself, probably just any toolbar, OpenStax is designed to provide quality textbooks accessible for free to people. So you go to OpenStax, there's textbooks for all sorts of courses. We're science, we're physics, for AP courses. I guess we're college physics. I guess they have them in other languages too. If you are fluent in another language that they have, you could maybe enjoy it that way. You can download the entire PDF of the book. You can download it in an app. You can view the book chapter by chapter online. So we're going to start in chapter 11. You can go ahead and jump to there if you like. I don't want that. And kind of go through the textbook. There's videos linked and some other things all right there for you. That's if you want to do it that way. The other thing that I did is I took the entire book and downloaded it as a PDF and then chopped it up into bite-sized PDF. So you can download chapter 11 PDF onto your hard drive if you want and read it, or right here in Canvas, they make it so you don't even have to leave the Canvas page. You can read through chapter 11. There's some links to probably some simulations that no longer work, but some that do, and you can go through the chapter that way. There's worked out examples. I believe on the OpenStax site, let me go back for a second. I think there is a place where you could access student resources. Student solution guide. I guess you'd have to set up a login to do it. There's no charge for it, but getting started guide, student solutions guide, just some resources that are right there on the website for you. If you think that might be helpful for how you learn things. I think I have the Canvas page set up in a way that is reasonably accessible to you and reasonable and organized. So if you're happy to go through things the way that I have them set up, then you needn't go to an outside website, but outside websites exist, and physics is physics. Some things have changed in the past 50 years, but a lot of things haven't. If you find that the way that I'm discussing something leaves you a little confused or whatever, and you want to go on to Khan Academy or just do a YouTube search for fluid, I guess we're doing statics first, fluid statics, and see what somebody else has to say on the subject and how they present it, that's perfectly all right. Sometimes it's helpful to hear things from a variety of sources. On that subject, I'll just point out that peer tutoring is available. I haven't communicated with the person who organizes the peer tutoring recently, sorry, to know exactly who is lined up to do peer tutoring for Physics 2, but they have changed the procedure for how to sign up for peer tutoring. So the PDF of the new procedure, which is going through the Navigate portal, is here for you, so you can do that. Typically what happens is that the tutor will put in what hours they're available to do tutoring. You will go in and sign up for a time, have a Zoom link, meet up with the tutor, go through any homework problems you have or any concepts that you're having trouble understanding, and they can help you work through it. If the way that I'm presenting material, going through things, leaves you a little confused, the peer tutor can maybe approach it from a different way that makes it easier for you to understand. I will also have office hours that I don't have posted here yet, but I will have hours if you want to meet with me one-on-one to talk about something. I will have the link for how to do that as well. So all sorts of supports are here for you if you need them. Just probably don't know for sure if you need them yet. Okay, before I get too deeply into things, I have set up an anonymous poll. I won't know who answers what. I'm just trying to get a sense of the pulse of the class, how people are feeling and doing, and level of preparation ahead of time. So I'm going to post the poll. Please take a few minutes and go through and answer these questions, and I'll be right back. All right, I'm going to end polling in just 15 seconds if we haven't gotten through with everything yet. Okay. So sorry to hear that some people are not doing so good. Overall, people are feeling okay. I ask about the general chemistry because there's a fair amount of familiar territory People who've taken general chemistry will talk about things like density and pressure. We'll go through the ideal gas law. So if you've taken general chemistry and those topics are basically familiar to you, you'll have some confidence in some of the topics we go through. A few people doing some other classes. It can be very busy in the summer, and it comes fast. But if you are able to manage your time well, it all should go okay. Almost everybody's working. That's life, I guess. We all gotta, eat and pay for things and also balance any courses we're taking. So just try to, as much as you can, manage your time so that you keep up with the course. It's really hard if you fall behind to be able to catch up, because you have to do everything that we're doing that week and also go back and do things from the previous week or something. And it's really hard to catch up. But if you can keep up, or maybe even work ahead a little bit, there's everything is posted. So you can, if you feel good about chapter 13 material and you want to start knocking off the chapter 13 homework ahead of time, because this week you have a little more time available than you do next week, then you can work ahead. Just make sure that you review the material before we have a quiz on that stuff if you do the homework ahead of time. We have some anxiety, not a ton. It has been my experience that people tend to feel pretty anxious about physics, maybe up until we get going. So if you took physics 1 in summer session 1, you're probably feeling okay. Hey, I know exactly what's going to happen here, and we'll keep chugging along. If you haven't had physics 1 in a while, or if you haven't had me for a class before, maybe there's a lot of unknown there and you're feeling anxious. And I appreciate that can happen. And, we'll try to calm your fears. Anytime during class, if you have a question, feel free to either unmute yourself and ask the question, or you can just type it in chat, and you can type it in private message chat, and I will kind of work the answer into the lecture discussion dialogue, so that maybe it's not obvious to other people that you asked a question, but that somebody had a question, and just if you're bashful like that. Honestly and truly, if you have a question, other people probably have the same question and are glad that you asked, but I understand if you don't want to be, on camera asking questions, if you, just are shy or bashful. The course is going to work. It's a set number of chapters. We don't do every detail in every chapter. If you want to know which parts of the chapter are most relevant for doing the homework and things that I'll ask on the exam, kind of go through the homework. The homework problems will set the parameters for the material that we're covering in that chapter. I tend not to ask any questions on a quiz or an exam if it's not something that we've discussed in lecture or lab or was covered by the homework. So you get a good sense of that. The homework questions are posted as Canvas quizzes. So when you go to do it, for the conceptual questions, they are posted, with like a multiple choice kind of format. For the actual problems, let me go back to a actual problem. Probably chapter 11, number 11 is a problem. The numbers in the question that you have will be different than the question that was actually, the words of this question are question number 11 from the end of the chapter for chapter 11. But I've got it set that the numbers change each time you do the problem. Part of the reason for that is you can keep doing the problem over and over again until you get it right. And what I hope for you to get out of that is work out the process, or reinforce the process of solving a problem like this, not just memorize what the right answer is and plug it in. So if I decided that I'm going to do this question and I'm like, I don't know, 1.59 times 51. It's always something like that in physics. So that's 8109. 8109. It's always multiply or divide or something, I don't know. So if I just did that for my answer and I submit my quiz, I would see that I got it wrong. And the real answer is 3,143,396. So goodness, I was way off. Maybe I should learn how to answer questions like this and not just multiply or divide. But so I tried the problem, and it's 1.59 square centimeters squared, and 51 kilograms. And then I decide to try it again. And this time it's 1.65 square centimeters and 58 kilograms. So if I just memorized the answer from last time and plugged it in, I would get it wrong again, because the numbers change every time. And so the answer is different. I have the Canvas quizzes, they call them quizzes, even though this is our homework. The Canvas quizzes are set up with a variable in place for the numbers, and I have a range set, and then I have a formula in there for determining what the correct answer is. I have it set with a pretty generous range of answers. So if you're off by a single decimal point, you won't get marked wrong. But the point is, each homework question is only a few points. It's pretty low-hanging fruit. It will show you the answer once you try it, but you can keep trying until you get the right answer, at which point it will only keep the highest score. So that's when you finally get it right, you will have full credit. Now, what if you're saying, well, I just have no idea how to solve this problem, chapter 11, number 11. Well, underneath the homework questions, the links to where you would answer those Canvas quizzes, underneath those is a link to a Canvas page called Chapter 11 Homework Videos. And if you scroll down to number 11, you can, I have them set up. One's like a YouTube, unlisted YouTube video, and some others are like discussions in I don't know, but you can play it, and it's me. I was experimenting with some video editing that I ultimately gave up on when I did this, but it's a younger version of me. Oh, this is number 15. Number 11. Oh, that was a bad thing to do. I gotta take those out. It's a younger version of me with my experimental video technology. Come on, get to it. And here I show up with a little less gray in my hair and beard, and I go through the process of solving the question. So that if you are like, I have no idea how to answer this, I'm not sure what to do, I will go through step by step, solving the problem the way that it appears at the end of the chapter. So the number that I come up with at the end here isn't necessarily the number that you will have as your answer, but the process, the step-by-step process is here. And you can add in closed captions if you wanna see what I'm saying, and you can speed me up or slow me down, depending how you wanna do that. And I will go through and work out the solution, and you will understand hopefully how to get to the answer. So anytime you're doing the homework and you're like, I don't understand how to solve this one, you can summon younger me to come help you work through the problem. So there's that. We'll go through chapter 11 today. And then on Thursday, I will say, hey, well, Thursday, I'll probably first say, hey, we're gonna talk a little bit about chapter 12 material, and I'll do a presentation on chapter 12. And then I'll stop and I'll say, hey, do you have any questions from the chapter 11 homework? And if you have any lingering questions on chapter 11 homework, you will ask those questions, and then I'll say, okay, now it's time for the quiz. The quiz will be questions very similar, maybe some are identical, but some are similar, some are a little bit different. Questions from the homework or similar to the homework, or something that we discussed in lecture, so that you can, be prepared for those things. And I'll say, okay, we're going to do this, it's the end, near the end of class time. Once you're done with the quiz, you can go. But near the end of class time, while we're here together on Canvas, I'll say, go ahead and start the quiz. If while you're taking the quiz, you have questions, like I don't quite understand what question number 2 is asking me, or, did you forget to give us data on the data sheet? There's something that I think I need to know that isn't there. I'm right here with you on Canvas, probably do private chat for that, because other people are here taking the quiz as well. But take the quiz, ask me any questions you have along the way. And your first time taking the quiz, your time taking the quiz on Thursday, you have, oh, so sorry for the noise. You have your calculator and the data sheet. I guess I can click on it. The data sheet that I give you for taking the quiz. Those are your resources for taking the quiz the first time. Data sheet, calculator, and access to me for kind of clarifying questions while you work on the quiz. After that, when you're done taking the quiz, there's probably one of the problems with Canvas quizzes and Canvas questions is that the system grades you as right or wrong. There's no partial credit. So after you take the quiz, your score is probably going to appear a little bit lower than it will ultimately really be. I will give you a chance to send your work. If you have a piece of scrap paper that you're working on while you take the quiz, as you write out the formula and solve for the proper variable and whatever, you can send me your work and I can award partial credit based on, you know, how close you were, what was going on there. But wait, there's more. After that, you have the opportunity to take the quiz a second time, open book, open note. This time you can use the outside resources to try to figure it out all the way. And what Canvas will do is keep the average score of your 2 quiz attempts. So homework you keep doing till you get a perfect score, and it will keep that perfect score once you do it. Quizzes, which we have during class time with me here with you, the first time, you know, obviously it's kind of got to be an honor system kind of deal, but I'm trying to figure out how well you understand the material if I have to re-emphasize something before the exam. So I'm asking you, no other resources besides the data sheet, your calculator, and obviously you can have some scrap paper to take the quiz, and we can see, you know, because that's the time when during lecture, I'll be going over something and you're like, yeah, that makes sense. Yeah, I get it, no problem. And then when you go to do the homework, you're like, oh, I don't quite understand that. And you can click on the video of me going through it and you're like, yeah, I understand that. I understand, no problem. And then when you go to take the quiz, even the very same question, you might find like, oh, dang, I thought I understood, but I'm missing a step or something. And so it's good to find that out on the quiz where it's kind of lower stakes before exam time. So you have multiple attempts on the quiz, but it keeps your average score. I'm not doing, you know, the lockdown browser and webcam and all that. I think we can just have some trust and honor system, and I'll deal with any concerns about that later, if there's anything going on. All right, so, and that's kind of how we'll move along through the course. So we have chapter 11 today, quiz on chapter 11 next time, chapter 12 next time, the quiz on chapter 12, the time after that. I gotta do away with these things where I say, kind of change the way I did it. We're doing it live in person. So, so I don't have quizzes due by sometime. I have multiple attempts. I cloned everything from last summer where looking back on it, I could have done it so much better. So I think we're doing things better now. Okay, labs. You click on the lab. I might need to update this. Yep, I need to update the lab. I will get that done. They did away with Flash Player with the new year. So there's another way to do this lab, and I will post it. But the lab is a set of questions that are related to the simulation that you'll do, and that will be the lab. So it's kind of a interactive simulation thing, but it's you know, a little different than actually coming into the building and doing a lab. Labs have due dates. I'm not going to have you come, for a specific time for us to do lab. If I can, I'll record a little video, kind of like a let's play video to help you, get an idea what you're supposed to do for that lab. But the instructions are generally pretty clear. So Archimedes principle, I actually went into the physics lab and I did essentially what you'll be doing for the lab, and then gave you some sample data. And then when you do the lab yourself, you will manipulate that data that I gave you and come up with some answers. Try not to fall behind. These things will keep coming. We'll have labs due, we'll have quizzes due, homeworks due. It's easy to fall behind in class. I understand how it happens. Life gets busy, but when you fall behind, it is so hard to catch up. So I'm encouraging you as much as I can just to not let that happen in the first place. If you can manage to keep up, or just keep up as deep into the summer session as you possibly can, then you'll just be in a better place. And I want you to be in a good, better place. All right, I am feeling at the point where we can start into the lecture time. Do people have any questions before we get underway here? All right, if you think of any questions, go ahead and type them in chat. Feel free to ask questions. So chat is there for you. You can click on the little tab to just send it straight to me and not everyone, or you can send it to everyone if you want to do that. But okay. Here we go. Physics 1, I always tell people, if you are really struggling with the concepts and ideas in the first chapter and the second chapter, it's only going to get worse, because the third chapter builds off of the second chapter, and the fourth chapter builds off of the other ones, and the entire course all the way through just keeps building on the foundation. Physics 2, the way Salem State does it, and the other school that has a very similar structure that I see is UMass Amherst. Different schools have different structures for how they do Physics 1 and 2, but we are most closely aligned that I see with UMass Amherst. And what we do in Physics 2, it's kind of two distinct segments of the book. So chapters 11 through 15 are ultimately building up to this world of thermodynamics. But in thermodynamics, there's a fluid that moves through the process. And so we start with an introduction to fluids, and we'll talk about pressure, and we'll talk about temperature and gas laws and all these different pieces that build together into this early 19th, 20th century steam engines, heat engines. That is how a lot of our technology that we currently use still work. And so there's heat engines, thermodynamics. It's a pretty coherent, reasonably connected aspect of physics. Then we have exam number 1 on chapters 11 through 15, and we will move on to electricity and magnetism. And electricity and magnetism is sometimes the entire topic for physics 2, the way some schools do it. We'll get into less depth than them, presumably, but it's just an introduction to electrons moving through a wire and electric forces and electric fields and magnetic forces and magnetic fields. And it's kind of an interesting thing, but it's totally separate from fluids and thermodynamics. So if you love the stuff for the first few chapters, that's great. If you hated it and you just barely got through the material in the exam, that's not the end of the world, because the second half of the course is totally different, a totally different thing. For that reason, I'm not doing a comprehensive final exam for this. We have exam 1 on the first half and exam 2 on the second half, and they're 2 totally separate things. Hopefully that's good. We require students to have had physics 1 before they take physics 2, largely for, there's some kinematic stuff, but kind of forces and gravity, weight, that kind of force material. Toward the end of physics 1, the chapters on impulse and momentum and energy and then rotational kinematics and dynamics, those don't play much of a role in physics 2. So if your physics 1 foundation or your physics 1 memory still has a little space in your heart for forces and weight and net force, something that's pulling down and pushing back up, that's the level of physics 1 that we're hoping that you'll still have, or at least not be freaked out by as we kind of move into it with the topics that we're covering. So, oh, come on, move to the next slide. I always have this slide in there when I'm teaching this in the spring semester. Hey, if you are graduating, whenever you're planning to graduate, it doesn't just happen automatically. You have to let the registrar's office know that you're planning to graduate. And even if you let the registrar's office know that you're planning to graduate and you think that you've completed every graduation requirement and your advisor thinks that you've completed every graduation requirement, that's all good, but it only really matters that the registrar also thinks that you completed every graduation requirement. And so they do an audit of everything that you've taken, and they'll sometimes come back to you and say, hey, we don't have on record that you did this thing. And maybe it's just a matter of department chair doing a substitution or something else, but it's fewer panic episodes and fewer concerns the sooner you find that out. Okay, now we're really getting into chapter 11 and some physics-y things. Let me admit, if you haven't heard this before, here's the confession. Physics is a little bit obnoxious. So I am sorry about that, but it's just the way it is. It's probably a little more obnoxious feeling to you if you're a biologist or a chemist, I don't really know exactly what units geologists use. So maybe they're not as annoyed as some other people. But if you know anything about density as a biologist or a chemist, you probably would know that water has a density of 1 gram per cubic centimeter, or maybe you would say 1 gram per milliliter. That would be the density of water. But in physics land, we don't use grams for mass. We use kilograms for mass. And we don't use centimeters for our unit of length, and therefore cubic centimeters for our unit of volume. We use meters. So in physics land, the unit for density is kilograms per cubic meter, which means that everything sounds strange. The density of water is 1,000 kilograms per cubic meter. Now, this is fairly easy for me to remember because my sister, I have no offense to English majors anywhere. I don't mean any offense, but my sister was an English major in college, which has nothing to do with the fact that she graduated and decided to start her own landscaping business. It just didn't match what she, but whatever. She started her own landscaping business. My sister is older than I am. So my summer job was working for my sister, and we would do landscaping. And oftentimes we would have like a trash barrel that we would use to haul things around a yard. So bark mulch would get delivered by a big, dump truck kind of thing. And there'd be a big pile of bark mulch in the front yard. And I'd go over with the barrel and I'd fill it up with bark mulch and I'd heft it onto my shoulder and walk over to the flower bed and put out the bark mulch around the plants. And then toward the end of the planting, needed to water the plant. So I would take the barrel over and I'd fill it up with water from the garden hose and I'd go to lift it up. Really heavy. Water is really heavy. It's very dense. 1,000 kilograms per cubic meter. I didn't have nearly a cubic meter volume, but a meter, I can't really show it. To the edges of my screen, a meter by a meter by a meter. A cubic meter is huge. It's a significant volume. And then 1,000 kilograms, you might not be as familiar with what a kilogram is relative to a pound, but 2.2 pounds in a kilogram. Kilograms are pretty heavy. So that's a heavy thing, a 1,000 kilograms per cubic centimeter. So here's a list. So if you're probably not used to densities in grams per cubic centimeter or grams per milliliter for anything besides water. So we can let that go. But here's some common densities for things that you might encounter in the world. Aluminum, brass, different metals are fairly dense. The kind of thing you want to judge by, is it more or less dense than water? So gases are obviously way less dense than water. A lot of metals are way more dense than water, such that they would sink if you put them in water. Ice is kind of a weird thing. It's frozen water, but ice is less dense than liquid water. So ice floats on the top of water. All my ice cubes melted in my ice water here, but they were floating on the top. That's why you have a layer of ice on top of a frozen lake or pond. It's not frozen all the way down through the bottom, but there's a insulating ice layer on top. Oil is less dense than water. Oil will float on top of the surface of water. And so there you go. Just some common densities to kind of keep in mind. Some of these examples are less useful, some are more useful. If you don't know the tricks and secrets of asking questions when there's an equation, so the equation we have, it's the Greek letter rho for density equals mass over volume. So there's essentially three questions, right? I could give you the mass and volume and ask you what the density is. That's a straightforward use of that equation. The way this question is phrased, you're going to figure out the mass given the volume and density. So that's rearranging. We multiply both sides of the equation by volume, and we get density over volume equals mass. The other question would somehow to be solved for volume, right? We solve for density, we could solve for mass, we could also solve for volume. So that's multiply both sides of the equation. Oh, sorry. I hate it when I lie to you by accident. It was an accident. If I multiplied both sides of the equation by volume, then volume would be in the numerator, not the denominator. Just like it is here, mass equals volume times density. And then the other thing would be to solve for volume all by itself. That's to divide both sides of the equation by density. And we'd say that volume equals mass divided by density. I don't know why you would encounter, these three different kinds of questions, but it could happen. And so in this example taken from the textbook, here's just a case. So the body of a man whose weight is 690 newtons contains about 5.2 times 10 to the negative third. If you are not comfortable with scientific notation, that will be problematic for physics 2, because we're going to deal with some very large numbers and some very small numbers. So I do want to spend a few moments talking about how to do scientific notation. You should have a calculator that you're on good speaking terms with. I say that knowing full well that my son rarely ever touches a calculator and types all of his calculations into a Google toolbar, and you just have to be really careful when you're doing that to not have, you can get an answer, but it might not be the right answer if you didn't put in the information correctly. So, what? Here we go. We want to find the blood's weight and then express it as a percentage of body weight. So if the person weighs 690 newtons and their body contains 5.2 times 10 to the negative third cubic meters of blood, the 690 doesn't matter just yet. So don't just take every number that appears in a question. That will be relevant for percentage of body weight, but it's not relevant for finding the weight of the blood. The weight of the blood, we can find the mass of the blood is the volume of the blood times the density of blood. That was on the previous chart, 1,060 kilograms per cubic meter. So on my calculator, I type in 5.2, and then on my calculator is a button that's EE, and I would hit 3, then the negative sign on my calculator. So just make sure you can get the right answer. If you do 5.2 times 10 to the negative third power, that should work, but somehow it doesn't seem to for a lot of people. So I put in 5.2 times 10 to the negative 3, like so, on my TI-30X calculator, and it then reads 0.0052 because I don't have my calculator set to scientific notation. And then you multiply by 1060 and you get times 1060, 5.512, and the unit is kilograms. Now, the 5.2 times 10 to the negative third implies that you only have two significant figures. So rounding off to 5.5 kilograms makes perfect sense. I'm not going to be a monster about significant figures. So if you answered 5.51, you would not get marked wrong, especially the way it's set up on Canvas. I have I either do plus or minus 10% or plus or minus, some number. So it will accept a range of answers as correct so long as you did the basic process correctly. Clear all drawings. So if we wanted to get the actual weight of that blood, 5.5 times 9.8. That's the thing from Physics 1 that, if you don't remember that, you would have to relearn it. Mass is one thing. Mass is a scalar quantity in kilograms, but weight, what is the weight of the blood? Weight is a force in newtons, and anything here near the surface of the Earth is being accelerated downward by the acceleration due to gravity. And so mass times gravity, acceleration due to gravity is 9.8 meters per second squared. So mass times gravity gives you 54 newtons. It's how much the blood in this person weighs. And then as a percentage of body weight, that's when we go back and use the 690 newtons. 54 divided by 690 times 100% to get a percentage. 7.8% of this person's body weight is their blood. Okay, that's density. Set that aside for a moment. Now we move into another similar looking concept, talking about pressure. Again, here we go. Physics is obnoxious. It's different units than you're used to using if you are a chemist or a biologist. If you're a chemist or a biologist, you say, oh, the atmosphere gives us pressure. It must be 1 atmosphere. And that's, a legitimate type of pressure. But in physics, we don't do that. Pressure is force divided by area. Force is in newtons. Area, again, we do meters for everything, so it's meters squared. So the unit of pressure is newtons per meter squared, which they named after the scientist Pascal. So we do PA for that, capital P, lowercase a. So again, we have the world where I could possibly ask you 3 different kinds of questions. So if I gave you force and area, you'd tell me what the pressure is in pascals, making sure that the force is in newtons and the area is in square meters, not centimeters. So you might have to convert from centimeters squared to meters squared, which was kind of the punchline of number 11 from this chapter. I could multiply both sides of the equation by area, and I'd say pressure times area equals force. And maybe I'd be solving for force. Or In some bizarre world, maybe you're solving for area. You'd say area is force divided by pressure. So the three kinds of questions you could possibly get using this simple three-term equation. That's just one of the things that you can kind of anticipate what might be going on. Clear, close, switch to the next one. So no animated drawings of people died in making this image. Kind of looks like this person is floating somewhere beneath the water, just having some fun. She'll come up for air soon. And for whatever bizarre reason, we're actually focusing on this person's hand. Suppose the pressure acting on the back of the swimmer's hand is 1.2 times 10 to the 5th pascals. This is a very big number rather than a very small number. And then the area, 8.4 times 10 to the negative 3rd, that's a very small number. So again, make sure you can go through the steps of a calculation and get the same answer to know that you're able to do scientific notation correctly and get the right answer. So determine the magnitude of the force that acts on the person's hand. So pressure is force over area. So force is pressure times area. So the force is going to be magnitude of the force. Magnitude is just the number. A vector quantity has magnitude and direction. So whenever they say magnitude, they just want the number. I know it sounds like it's bound to be more confusing than that, but it isn't. So 1.2 times 10 to the 5th pascals times 8.4 times 10 to the negative 3rd square meters. That's a negative sign. Just make sure you can do these calculations and get the right answer. So I'm doing 1.2 times 10 to the 5th. That's a big number, times 8.4 times 10 to the negative 3rd. That's a small number. And when I multiply a big number and a small number, I'm getting 1,008, what is this, newtons? And so typically what you would do if everything else is in scientific notation and you have a question about how many sig figs, I would say 1.0 times 10 to the 3rd newtons. One of the good things about scientific notation for your response is that it's unambiguous with the number of significant figures. Again, I won't get on your back about that, partly because Canvas is a little bit obnoxious. There's no way to type in scientific notation, or at least not a good, reliable way to do scientific notation in Canvas. So I have it set up that you just report, you'd report the 1008 or the 1000 answer rather than reported in scientific notation, only because the system, will mark you wrong if you have the right answer in a different format. So I don't know if I have the answer. So yeah. Vectors have magnitude and direction. Force is a vector quantity, but if you're underwater, force will push on an object in all directions such that perpendicular to the surface, so the top of your hand will feel a downward force, the palm of your hand would feel an upward force. That's just how pressure works underwater. But we'll talk about that. We're getting there. All right. we don't always appreciate that we are under a lot of pressure. So the chemistry and biology unit for pressure, on a typical day, not a low pressure system or a high pressure system, we would just kind of say, oh, that's 1 atmosphere of pressure, which is a fine way to do it because that's what we typically experience. In terms of newtons per meter squared, the Pascal unit of pressure that we use in physics, that normal pressure that we're feeling right now in atmospheric pressure is actually a huge number, 1.013 times 10 to the 5th Pascal. So 101,300 pascals is normal atmospheric pressure. There are some pretty impressive videos demonstrating the force that is accessible from that much atmospheric pressure. If you've seen those giant barrels, giant metal barrels that different industrial amounts of stuff are delivered in. I've seen videos, we can probably find one on YouTube if we want to, where somebody sealed it up really well and pumped out all the air. So if you pump out all the air, you leave a vacuum. So the difference in pressure, the atmospheric pressure on the outside and very low pressure on the inside, means that there's a huge force, 101,300 newtons of force pushing on all sides of the barrel. And apparently it sounds very much like an explosion when it crumples due to atmospheric pressure. Atmospheric pressure is a significant amount of force per square meter area, but we're not crushed like grapes because we have internal forces. All of our cells have a certain amount of force pushing out, equal and opposite, typically, to atmospheric pressure. It does leave us susceptible to feeling weird if the pressure outside drops a lot or increases a lot. You can feel it if you dive down to the bottom of a deep pool or way down deep in a lake. The deeper you get, the more pressure you feel. Oftentimes you feel it on your eardrums. You can feel high pressure. There's also situations where you can feel a little off, pretty bad, over low pressure. There's that. This figure depicting a box of water submerged in water has appeared in every physics book I've ever seen or used. It's a very weird idea that they're trying to convey here, and everybody does it exactly the same way. So remember, we talked about pressure. Pressure is force over area, which means force is pressure times area. So there's two different spots where we might look at this cube of water that is sitting in the middle of the water. And one part is down deeper. If it's deeper, then the pressure here will be bigger. And if it's shallower, the pressure will be less up at the top. And so the net force in the y-axis acting on this cube of water submerged in water, the net force is pressure 2 times area minus pressure 1 times area minus the actual weight of the water, which would be pulling it down. So the net force actually equals 0. The cube of water submerged in the water. I'm getting a phone call, sorry. Don't let it distract you. Is not moving up or down. Now you could probably imagine if you've ever been in a body of water with like a beach ball or I don't know why you'd have your volleyball in the pool, but you know, some sort of ball filled with air. If you push the ball under the water and let it go, it shoots up to the top again. There's a force acting on it. Why? Because the ball doesn't weigh that much. Oh, so annoying. Hold on one second. Sorry about that. So there's a difference in pressure the deeper you go, and that pressure gives rise to a force. And if the thing has significant mass, then maybe that net force is negative. If you have a rock in the water and you let it go, it will sink down to the bottom. But if you have a ball filled with air in the water, it will feel a force that will pull it up to the top. So the punchline here, the extra little bit of information that we have is that mass of the object is volume times density. Remember how density was mass over volume? So mass equals volume times density. So we're going to plug that in to this equation that we're ultimately developing here. So P2A, the pressure down deeper in the water times the area, P1A, plus we plugged in rho V for the density of the object and the volume of the object times the acceleration due to gravity. And then we do another substitution. Volume is just area times height. It's the volume of any kind of cube. So P2A equals P1A plus rho density, A area, HG. Wait a second, area appears in every term? I can cancel that out. So we get this new equation. Either believe what I just said to you or just jump to the new equation, take it on faith and use it. P2, the density down deeper, equals P1, that's either the pressure at the top or the pressure above the surface of the liquid, plus rho, I usually do rho GH, I guess that's alphabetical, rho GH, density of the object times the depth times the acceleration due to gravity. Don't need to use this example. As you go deep into water, you will find that the pressure is the same everywhere. All that matters is depth. P2 equals P1 plus rho GH. The only thing in there is H, is the depth in the fluid. P1 is atmospheric pressure. There's atmospheric pressure pushing down on the surface of the water, And then as you go deeper in the water, it's the density of the water, which is 1,000 kilograms per cubic meter, times G, 9.8 meters per second squared, times your depth underneath it. So atmospheric pressure would be 1.01 times 10 to the 5th pascals. If you dove down 5.5 meters is really deep. If you dove down really deep, you would increase that pressure significantly to 1.55 times 10 to the 5th pascals. All right. We measure pressure all the time. If you hear it on weather reports, there's a high pressure system here that's keeping another front out, or we're moving into a low pressure system, so expect some storms. One of the ways that pressure would be measured is to have a cylinder full of mercury liquid. Mercury is a metal that is a liquid at room temperature. And so you'd fill the tube with mercury liquid and then invert it into a pool of mercury, and atmospheric pressure pushing down on the surface of the pool would have the mercury rise or fall within the evacuated tube. And so one way that you'll hear pressure referred to sometimes is millimeters of mercury, and that's just the height of atmospheric pressure for this tube to be lifted. And then if the mercury is rising or mercury is falling, that's reflecting a change in atmospheric pressure. We don't do millimeters of mercury. We don't do atmospheres. We do pascals for our unit for pressure. But there are other ways of doing it. One of the weird things, maybe just to know, is if you are checking the tire pressure for your automobile tires, it's not telling you how much pressure is inside your automobile tires. It's telling you the gauge pressure, and the gauge pressure is the pressure over and above atmospheric pressure. So typically here in the United States, because we're weird, we do pounds per square inch, which is like doing kilograms per cubic meter, but with the antiquated pounds instead of kilograms and square inch instead of square meter. So that's just the way we do it. But if it's 32 PSI, pounds per square inch, that's not literally the pressure inside your tire. That's the pressure inside your tire above atmospheric pressure, just so you know. Blood pressure. I'm not sure I know what units blood pressure is in. Maybe it's PSI or millimeters of mercury. I should find that out. I'll check that out sometime, but that's blood pressure. It's just another kind of pressure. Okay, here's a little handy dandy tool for you to think about. This is a ridiculously scaled diagram, but it is depicting this pretty neat thing. If you exert a force into a liquid that is sealed, so a self-contained liquid, that force will exert pressure throughout the liquid undiminished. So if we have a small area region and a large area region, what we're ultimately able to do is magnify a little force into a big force. If you have ever had the joy of getting a flat tire, you pulled out the little hydraulic jack that comes with most cars, you were doing something like this. If you actually look at the jack, there's a small part where your handle is for pumping it up, And then there's a larger cylinder where it's actually lifting up your car. And you're, pushing down on the jack, and your amount of force is being magnified several times over to actually raise the car. And if you take your car in to be serviced and they lift it up on a lift, they're using a hydraulic system like that as well. What it's doing is making use of this idea that pressure is force over area, but we have two different areas, so we can magnify our force. F2, the force that is actually lifting the car up, is going to be F1, that's the force that you're inputting, times area 2, it's a big area, divided by area 1, a smaller area. So if the two areas differ by a magnitude of 10, then you will magnify your input force by a factor of 10 to lift it up, or maybe 100, all different amounts possible. So here's going through the process with a set of numbers, and then you can see that for your input, I guess for the output force, it only takes 131 newtons in order to lift a car that weighs 20,500 newtons. Area for a circle is pi r squared. So there are some things that will pop up through the math that we do where you're going to be like, oh yeah, so radius is 0.012, but area is pi r squared. If I don't think to give you that equation on a quiz or an exam and you realize you need it, that's a perfect time to do the chat feature. And if I realize that I forgot to put it on the equation sheet, I can put that information out to everybody taking the quiz, but don't just sit there and suffer. If you're like, wait, there's an equation and I forget what it is, can you remind me? I am generally happy to do that. Okay, we had our cube of water submerged in the water. Another thing, this is a cylinder submerged in the water. All the same rules are in effect that we talked about before, but here we have a case where the object could float or could sink. And it can either float or sink, but it will do that with some amount of force acting on it by virtue of being submerged in a fluid. So this, I guess, is submerged in water. And there's a force, we call it the buoyant force. And so F sub B is the buoyant force. The buoyant force will act in the positive y-axis direction. It will push the object up. Now, if I have a big rock and I put it in the water, it will still sink, but it will sink while there is a force pushing up on it as well. So the force that's pushing up on it is the density of the fluid times the volume of the object times the acceleration due to gravity. So if I'm in the lake with my kids, sometimes my kids get a thrill out of holding me so they can, pick me up. I can, rest in their arms and they can walk around in the lake holding me up. Now they couldn't hold me up standing on land. There's no buoyant force, but I have mass, I have volume. So the buoyant force, the difference between my weight in air and then my weight that they feel in water is the density of the water times my volume, or at least the volume of my body that is underneath the surface of the water times the acceleration due to gravity. And the difference between those two makes it so that you can go to your friend who you might not normally be able to pick up on land, or at least it would take a lot of effort, but under the water, you can pick them up and hold them, and it's not so bad, thanks to the buoyant force. So Archimedes' principle ultimately gives us this concept that the magnitude of the buoyant force is the weight of the fluid that is displaced by the object. We have a lab. Is it the lab that I have the little video for? We have a lab that kind of goes through this idea and hopefully will make it a little more clear. So some objects, like a beach ball or a cork, might bob right on top of the surface of the water. Other things like a log, you drop a wooden log into the water and it sinks down quite a way before it starts to float a little bit. So most of it is submerged, and the point at which it starts to float, or the depth to which it sinks before it floats, is that point where the actual weight of the object is exactly counterbalanced by the buoyant force. Buoyant force is the weight of the volume of fluid that is displaced by the object. So it sinks until it has displaced its own weight in water, and then it will start to float at that point if it's not fully submerged. So there's that. Other examples. And then you will find that my PowerPoints are really long because I take all the images from the OpenStax book and copy them, and then I add some things to try to make it make a little more sense. So don't stress out if you go to look at a PowerPoint and you're like, oh my goodness, there's so many slides. That's not always the case. So we have some homework problems associated with chapter 11. Those homework problems are, you can click on the Canvas page to do them. If you go to this page and you click on the problems themselves, you will find that it's linked to another version of the course, and that can be problematic. So I will delete those links from this page just because it needlessly confuses people. So when you do the homework problems, do them from the main Canvas page, or I will show you other ways to do it. But when you want to watch the videos of me working through the solution to the problems, those are linked here for you. Save. So the homework problems are approximately how does density of air vary with altitude? It's pretty much just like it is with water. You get more dense the lower you get in water. You get less dense the higher you get. Same deal with air. Ice cubes melting in your glass. Same ship float higher or lower in seawater or fresh water. And I'll go through that with you. To measure the density of an object, you need to know both its mass and its volume. So if we figure out that it displaces 89 cubic centimeters of water, then it must have a volume of 89 cubic centimeters. So we could convert that to meters cubed if we wanted to do it that way, or we could just report the density in grams per cubic centimeter as another option. Pressure is force over area. So we have force, we have area, we can figure that out. I'm not sure how Canvas is working with scientific notation, so it might be better to just type out the whole number, but you can fit P2 equals P1 plus rho GH. Rho is the density of seawater. G is 9.8 meters per second squared. H is 11 times 10 to the third meters. A kilometer is 1,000 meters. Here's the depiction using the Archimedes principle. Again, area is pi r squared. Radius is diameter divided by 2, and you'll want to convert that into meters rather than centimeters. So some of these problems are just a fair amount of work just to get everything into the right units. 1 atmosphere is 1.012 times 10 to the 5th pascals. And the rock in air and submerged in water, you can figure out the buoyant force. So I think you are prepared to tackle these homework problems. You have videos of me walking through the solutions with you, if that is helpful to you. And on Thursday, we'll start our class time with me talking about chapter 12 material, getting you prepared to do that homework. And then we'll take a few moments, collect our thoughts, and I'll say, okay, do you have any questions from the chapter 11 homework before the quiz? And you'll ask me those questions if you have them before you start on the quiz. On our Canvas page, there are ways, let me switch to student view. There are different ways, I don't have everything active here, but if you go to assignments, you'll see every assignment from the course, and you can click on anything there and do them. If you click on syllabus, you'll have it's called course summary, but due on Thursday are these chapter 11 things, and we'll have the quiz on Thursday. And then chapter 12 quiz isn't on Thursday. I'll adjust that. Sorry about that. Do the following Tuesday, okay, is chapter 12 quiz and the chapter 12 homework. And I have these surveys in here just to kind of see how you're doing and see if I should adjust how I'm presenting stuff to make more sense to you. But in any of these locations, you can click and do the problems from there. Lab 1 and Lab 2 aren't due until a week from Thursday, so don't put those off indefinitely. If you're feeling ready to do them, get underway as soon as possible. I do have to update the buoyant force lab, but I will do that right after we sign off. I am recording this lecture. I will post the video once it processes. It takes a little while for Zoom to post the video for me to then use, and then I convert it into a YouTube video so that you have ease of captions and speed up or slow down, whatever you want to do. Since we don't have a quiz today, we're done earlier than we would normally be. So take that as a gift. Go ahead and tackle chapter 11 homework as soon as you're feeling ready, and be prepared with any questions you have on it for Thursday. I will post the video as soon as I can, and I think that's all we need for today.
Thank you.
If you have any questions, go ahead and ask. Otherwise, have a happy day, and I will see you on Thursday.
Thanks, Professor. Have a good one.
Thanks, you too.